Okay, let's talk a little bit about radioactive decay. If the proton to neutron ratio gets out of proportion so that the nucleus isn't stable, you can't get enough binding energy to hold all those positively charged particles together, you get a decay. The type of decay depends on what the particles are there, how many protons and neutrons do you have, and there's a band of stable nuclei called the band of stability. If it's in that, they're non-radioactive. So it depends on where you are relative to that, what you're going to get. The radioactive particles are emitted with kinetic energy, and it relates to the change in the binding energy of the products compared to the reactants. So here you can see the band of stability. That black line represents a 1-to-1 proton to neutron ratio. Notice it bends upwards, which means there's more neutrons per proton to stay in that band. It starts 1-to-1, kind of for the small ones, then 1.2, then 1.4, then 1.5. It definitely bends up. If you're neutron rich versus neutron poor, that determines which type of reactions you're going to see. So if you get too many neutrons, you're going to react in a way that's going to produce more protons, like, for example, beta. So if you look, the conservation principle is going to hold when you get these decays, the number of the mass number, the total mass is going to match up. That is the mass number of the A, and the sum of the atomic numbers has to match. For balancing purposes, we'll give an electron a balancing number for the atomic number of -1. So if that Q decays to form R and Y, then M1 has to equal M2 plus M3. And then the bottom number, Z1 has to equal Z2 plus Z3, where M's are the mass numbers and the Z's are the atomic numbers. With the iodine 131, an electron is emitted, that's beta minus emission or beta emission. We sign that again an atomic number of -1 for balancing purposes. The total number of protons and neutrons before must equal the same number after. So there's several different types that you can consider. The big three are alpha, beta, and gamma. Alpha radiation, you essentially lose 2 protons, 2 neutrons, or the equivalent of a helium nucleus from the nucleus. Beta radiation, you lose a high energy electron from the nucleus. Essentially, a proton becomes a neutron. The gamma radiation is a high energy photon from the nucleus. That's like gamma radiation that we talked about in the first semester course, but it's usually the result of some other decay, and then the nucleus is left in an excited state. There are very few pure gamma emitters. Usually gamma is associated with some other type of radiation. In nuclear chemistry, we find that a neutron can become a proton and electron. That's our beta emission. If you have too many protons, one of the things you can get is positron or beta plus emission, or you can get electron capture. And sometimes those last two occur in competition with one another. But one's going to give you more protons if you get too many neutrons, and the other one will give you more neutrons if you have too many protons. But a positron is a particle that's the same mass as an electron, but it carries a positive charge instead of a negative charge. We're going to look at several different radioactive decays, and I've copied them all into paper for purposes of working through them. So here they all are, and we're going to write out the different types of decays. So if uranium, and I went ahead and wrote all the atomic numbers as subscripts so that we could just get everything through. So it's going to decay to something plus an alpha particle, which is 4,2He. So if it's got to add up, 238 minus 4 is 234. 92 minus 2 is 90. And then we need to look on the periodic chart and find element 90, which is thorium, which is actually the substance for the next reaction. So if it's going to beta decay, it's going to decay to something plus a beta. So -1, 0, lowercase e, remember lowercase symbols are subatomic particles, where if you start with a capital letter, then that's going to be an element. So 90 minus a minus 1, so it's going to be 91. The mass doesn't change, so 234. So again, we're going to look, it goes up to 91, so PA. Even if you don't know what that element is, and you may not for some of these radioactive ones unless you've memorized them all, it doesn't matter, just put in the symbol. Emission. If you see that M, they call that metastable. And so there's a quasi or metastable excited state that lasts longer than a normal excited state, say for an electron. So to go to technetium 99 plus a gamma. And that's just light. Some people do write 0, 0, but that's not strictly necessary because that's just light being given off. It's hard to predict whether you get gamma or not. Sometimes you have to look it up to see if you get secondary gamma off of some other type of decay. If you're going to emit a positron, it's going to go to something, and then you're going to have that 1, 0, E, but that's a positive one, not a negative one. So that's going to be 5, 11. So 5 plus 1 is 6. So element number 5 is boron. So we'll put the symbol in. Electron capture. Now for electron capture, the electron is over here, and it's going to be captured in the nucleus. Usually electron capture comes with the emission of X-rays as well because of the transitioning. It snatches one of the inner electrons, and then the cascading effect of electrons coming out of the hole usually emits one or more X-rays. But it's associated with electron transfers and not. So 19 minus 1 is 18, still 40. So 18 is argon. And it's hard to predict that, but you're likely going to get an X-ray. One or more X-rays. So that's how you go about balancing some of these decays.